Structural patterns. These patterns help in composing and organizing classes or objects. Marker interface. Names and tags are a common way of identifying objects, but strings are often prone to typos, particularly if you have to use them more than once. Similarly, it can be hard to keep track of ID numbers or hash values and know exactly what they refer to. Instead, a marker is a class or interface attached to an object and is used solely or primarily for identification. It can start off as empty and later evolve to have additional logic in it. By using a type instead of a string or number, most IDEs should alert you if there's an issue. Markers can be turned into components or derived from using inheritance. They are a great way of filtering your searches when you need a particular type of object, especially if you name them well. The adapter pattern. If you've ever tried to plug a 3-pronged device into a 2-pronged outlet, you know you need an adapter. Similarly, this pattern acts as an intermediary, translating one interface into another that your system understands. For example, in game development, you might need to integrate an external library with your game engine. The library might have a different API than your system expects, so you create an adapter class to bridge the gap. Begin by defining the target interface your system uses, then implement an adapter class that translates requests into calls that the external library understands. While this pattern ensures compatibility, it can often add overhead if overused. The bridge pattern. If a class has 2 or more dimensions along which it can inherit, the bridge pattern attempts to split these and rely on composition instead, such that one becomes dominant and simply references the other. For instance, objects might be classified by shape or by color. An object that can't inherit from both groups will need to pick one to be the base functionality, in this case shape, and that class will then have a reference to the other. In this case, all shapes have colors, but not all colors necessarily have shapes. Usually, this is best resolved by considering that inheritance describes what a thing is, whereas composition describes what a thing has. While the bridge pattern is quite flexible, it's best reserved for larger projects. The wrapper pattern. A wrapper is a way to enhance an object's behavior without altering its underlying code. Child classes can often serve as wrappers by implementing both the base functionality and additional behaviors as well. Alternatively, we can make a new class or method that performs all of our desired logic plus something else. This can be especially useful if, for some reason, you don't have access to modify the original class or method, or if modifying it would break other parts of your code that depend on its current implementation. For instance, we might have a log system that writes messages to the console. Supposing we want to add timestamps and other data about a particular log. Instead of rewriting the original logger class, we create a wrapper class with a method that adds timestamps to the original message before writing that to the console. While useful for minor changes, excessive wrapping can obscure the original logic. The decorator pattern. A form of wrapper laid over top of an existing object. Decorators are designed to compound their effects, dynamically adding or removing layers of complexity. Picture a game where a character can gain temporary buffs like speed or strength. Instead of hard-coding every combination of buffs, you wrap the character in decorators that modify its behavior on the fly. Start with a base interface, create concrete classes for each behavior, and stack them as needed. This pattern is highly flexible, but can lead to confusing code if too many layers stack up. The facade pattern. Complex systems can often have too many moving parts for a user to manage. The facade pattern is a wrapper that simplifies things by creating a single entry point. For example, when building a save system for a game, you might have separate classes for writing files, compression, and encryption. Instead of calling them all individually, you build a facade class that handles the whole process with a single save method. While it makes the system more user-friendly, the downside is that it can hide too much detail, leading to less control. Facades can also run the risk of violating the single responsibility principle if tasked with doing too much. Extension object pattern. Extensions allow a class or type to be modified even after it's been compiled, meaning we no longer have access to change the underlying base code. Both adapters and extensions can be used on software that's already been developed. Where adapters allow us to link to existing features, extensions let us create brand new ones. For instance, extension methods are static methods belonging to a type or class that allow us to tack on additional functionality. A type like int or string cannot be modified, but their behavior can be extended, such as int.add1 or string.sort characters alphabetically. The flyweight pattern. Memory usage can balloon when you have many similar objects, like thousands of enemies on the battlefield. The flyweight pattern reduces this by sharing common state across objects. For instance, instead of storing redundant data like enemy types and textures for every enemy, you keep one shared copy and link each enemy to it. Begin by separating intrinsic or shared properties from extrinsic or unique ones. Then, create a factory to manage the shared state. This pattern excels in efficiency, but adds complexity in managing the shared resources. The proxy pattern. Sometimes you need a stand-in for another object to control access, improve performance, or add functionality. For example, in a multiplayer game, you could use a proxy to represent computer-controlled opponents or players not currently loaded into memory. The proxy provides placeholders for data and loads the actual object when needed. Start with an interface that the proxy and real object both implement. The proxy then forwards calls to the real object as needed. This can save resources, but introduces a slight performance hit when changing over. The dynamic proxy pattern. A specialized variation of the proxy pattern, where the proxy object is created dynamically at runtime, often using reflection or similar mechanisms. It allows you to intercept and control interactions with an object without modifying its code. For each real object, no explicit proxy class is written, but a single generic proxy mechanism can handle multiple objects or interfaces. For example, let's say that you have a service class. You create a logging proxy that takes the service as input, logs when a method is called, and then forwards the call. This pattern is great for auditing, security checks, or caching, but it can make debugging harder since you're working through layers of abstraction. The module pattern groups related variables, methods, and other logic into a single cohesive unit called a module that encapsulates functionality. It provides a way to organize code into reusable, maintainable, and self-contained modules. Modules typically expose only the methods and properties needed by the outside world, keeping their internal details private. Once a module is defined, it can be difficult to change as other systems come to depend on it. Modules can also risk becoming interdependent on other modules. Component patterns. Many object-oriented programming languages do not allow you to inherit from multiple sources. For this reason, composition is often preferred, which means we add behaviors to objects as they're needed, building them up like Legos. These patterns revolve around that concept. The composite pattern. A way of structuring code in which an object's data and logic are distributed across multiple components. It starts by defining an interface or base class, often called component, from which other classes will derive. Objects then maintain a list of all required components and can reference them as needed. Helper functions can be created to add, remove, or retrieve components, granting access to various properties and behaviors. One challenge of this pattern is ensuring uniqueness if an object has two or more of the same type of component without a means of distinguishing between them. The process of adding and removing components at runtime can also be computationally expensive. Component-based design. A paradigm where functionality is broken down into reusable modular components. Unity Engine relies heavily on the component pattern as a core design feature. All game objects maintain a list of components attached to them. The MonoBehavior class extends a class called Component, which allows developers to add or remove behaviors to and from objects, either directly through code or by manually dragging them in the inspector, which is often much more intuitive for non-coders. Entity Component System, or ECS. A component-driven design pattern that separates game entities into data, functionality, and systems that operate on them. Here, data are called entities, and functionality is stored in components. The organizational structure of this pattern can be more difficult to learn compared to other, more intuitive approaches. ECS is used for high-performance games or simulations that need scalability, like handling thousands of objects at the same time. Besides its normal component-based design, Unity Engine also has a built-in ECS solution intended to work with its jobs and burst compiler packages. Component-oriented programming. A refined ECS-like pattern where components focus more on encapsulating logic alongside data rather than being purely data-oriented. It can extend ECS with more robust behaviors, used to create reusable, modular behavior on individual entities, or more straightforward entity management in simpler projects. This pattern can blur the lines between data and behavior, and lead to more complex dependencies over time. If there are any design patterns you think we missed, let us know in the comments below. If you found this video helpful, please make sure to like, share, and subscribe so you stay up to date when we release new content. If you'd like to learn more about programming and game design, click on the link appearing on your screen now, or see the description below for ways you can help support this channel. Thanks, and take care.